Hello friends, welcome to session 13, Proofs and Important Results. Now, in the last few lectures on the theory of learning, we have postponed going over some of the proofs so as not to deviate from our mainline arguments. It's now time for us to look at some of those proofs. And in addition, we will also look at some important results that will come in handy later on during this series. So let me place this lecture in the context of the overall series of lectures that we are going to go through. Now remember, we began by talking about linear models. We began talking about linear models because those are in a way the simplest kind of models that are available to us, and we spent considerable amount of time on those linear models. We talked about linear classification, we talked about linear regression, we looked at things like the gradient descent algorithms, normal equations, and so on and so forth. And then after looking at linear models in great detail, we moved on to the theory of learning. In the theory of learning, we developed certain core concepts in learning. In particular, we looked at things like growth functions, we looked at VC dimensions, we developed the PAC theory, the probably approximately correct theory. Then we went on to the bias variance analysis, and finally in the last lecture we looked at regularization and validation, right? So that is what we have done in the theory of learning. What we are going to do after this lecture is move on to models and techniques. Okay, so in a way, after this lecture we are going to pivot. This is an inflection point. We are going to pivot, and we are hereafter we are going to go into models, the different models and techniques that are used in practice in AI while implementing algorithms. So here is where we are at the moment. This is where we are. This is the last lecture in the theory of learning, and therefore it is important. It's important for us to close the chapter on some of the key proofs and also look at some results that will come in handy going forward. So that is where we are in our lecture series, and that is why this lecture is important. Okay, so what is the agenda for today's lecture? The agenda for today's lecture comprises several results. The first one is the Hoeffding's inequality, which we have seen. It's a result from probability theory, which relates the bin frequency to the sample frequency. We remember what Hoeffding's inequality was. We will look at this. Spend a little bit of time looking at Hoeffding's inequality today. We will then go on to Sauer's lemma. Sauer's lemma was a key building block in the development of the generalization bound, right? You remember Sauer's lemma, and we are going to spend considerable amount of time proving the Sauer's lemma. We will then go on to this result that said that the VC dimension of a binary linear classifier equals the degrees of freedom. Now, this was an important result because it helped us to develop our intuition for what complexity of model could possibly refer to. It could possibly refer to degrees of freedom. That's why this was an important result. And we are going to spend some time on this result. Finally, I am going to talk about Lagrange multipliers and an extension of Lagrange multipliers to KKT conditions. KKT condition stands for Karush-Kuntaker conditions, and these come into play when you are talking about constrained optimizations, which is something that we may have to deal with in the future in this series. So we are going to talk a little bit about that. Now, I said this lecture was about proofs, but we have to draw a line somewhere, right? I mean, I've said in the past that AI techniques borrow heavily from other disciplines like probability theory, statistics, numerical analysis, and so on and so forth. And you end up having to draw a line somewhere. What are the proofs that we are going to dive into in detail, and what are the proofs that we are going to sort of just give references to? So the way I am going to go about this lecture is to say that any result that is borrowed from another discipline we will give references to, okay, so that those interested can do a deep dive, and we don't end up spending many hours on those results. And the results that are specific to AI, specific to AI theory or the theory of learning, those are the ones that I will give the proofs for in today's lecture. So what that means is that the Hoeffding's inequality, which is a result from probability theory, or Lagrange multipliers and KKT conditions, I am going to talk about these but give references to their proofs. And the Sauer's lemma and the VC dimension of binary linear classifier, since these are core results in AI, I am going to actually go over their proofs. So that is the plan for today's lecture. Let's get started. So the first result, like I said, is the Hoeffding's inequality, and it is a result which is a part of what are known as laws of large numbers. So if you are looking to do a search, you can search on the laws of large numbers and you would find Hoeffding's inequality there, and you can take a look at it in detail. What was the Hoeffding's inequality? We began with a bin with infinite number of red and green marbles. We said that we had a bin with infinite number of red and green marbles, out of which we selected n marbles at random. So we drew n marbles at random from this bin. We defined mu as the bin frequency, which was the probability of getting a red marble from this bin, and nu was the sample frequency, which is basically the ratio of red marbles in these randomly drawn marbles. So in this sample, what is the ratio of the red marbles? The Hoeffding's inequality told us that the probability of absolute value of mu minus nu being greater than a given epsilon is less than or equal to 2 e to the power minus 2 epsilon square n. This is what the Hoeffding's inequality told us, right? And Hoeffding's inequality was, we said, a fairly general result because it applied for all ratios of colors. So it does not matter, it applies no matter what the ratio of red and green marbles in this bin are. It's valid for all n, in the sense you could draw any number of marbles from this bin and the Hoeffding's inequality would still apply. It is valid for all values of epsilon that you can specify. You could specify any epsilon, and epsilon appears on both sides of this equation. So this result holds for all values of epsilon, and clearly this result establishes a trade-off between n and epsilon. Now, why was this result important? This result was important because it showed us that as you increase n, you could bring mu and nu close to each other with higher and higher probability. So the chances of mu and nu being very close to each other would go up as n increases. Now this was it's a fairly intuitive result. You would expect that the ratio of red marbles to n, so red marbles divided by the total number of marbles, would approach the probability of getting a red marble from this bin directly, right? I mean, that is in a way our understanding of probability theory. But the importance of the Hoeffding's inequality lies in the fact that it establishes a numerical value. I mean, it gives a definitive relationship between n and the probability of mu and nu being close to each other. So that is the importance of the Hoeffding's inequality. And if you wanted to use the result, I mean, like I said, this result is from probability theory, and it could take potentially a few hours to explain this. But since this result is borrowed from probability theory, let me just give you some references. This is a link. I'll put this link in the description of the lecture as well. But this is a link where the Hoeffding's inequality has been proved. One of the places where it has been proved, or you could simply go to ChatGPT or any other online tool and give it a prompt asking for the full proofs of Hoeffding's inequality, and you would get it. So I'm going to leave it at that. It was an important result, so it's important for me to give references to the proof. although we will not be going over the actual proof itself. Let us now move on to the Sauer's lemma, and before that a quick recap. We went over all of these definitions in great detail a few lectures ago, but let's do a quick recap. Like I said, the growth function of a hypothesis set, we said, was mh of n was the maximum number of dichotomies that can be created by the hypothesis set on n points, right? So mh of n, which is the growth function, is the maximum number of dichotomies or labelings. You could also call it labelings, which essentially involves assigning +1, -1 or blue and yellow to each of the points, and the maximum number of dichotomies that can be created by the hypothesis set H on n points is the growth function of that hypothesis set. The break point of a hypothesis set was any value of n for which mh of n is less than 2 to the power n. Remember, 2 to the power n is the maximum number of dichotomies possible in an absolute sense, because given n points, you can have at the most 2 to the n labelings of those points with binary labelings, either +1, -1 or red, blue, etc., yellow, blue, etc. So the maximum number of dichotomies possible on n points in an absolute sense is 2 to the power n. And if you have a hypothesis set which is unable to keep up with 2 to the n for some n, that n is known as a break point of that hypothesis set. If k is the smallest breakpoint of a hypothesis set, then k minus 1 was defined to be the VC dimension. And the VC dimension also happens to be the maximum number of points that can be shattered by this hypothesis set. We looked at shattering in detail in that lecture, a few lectures ago. But k is the smallest breakpoint of the hypothesis set, means beyond the VC dimension, essentially the growth function diverges from the curve of 2 to the power n. So these were some of the definitions we have seen in the past. I thought a quick recap would be in order. And we also looked at certain examples of the 3 points, 4 points, etc. Looked at various labelings, and we arrived at the conclusion that mh of 3 for linear equations, we did this exercise for linear equations, and we said that for linear equations mh of 3 was equal to 8, which means that the hypothesis set of linear equations could shatter 3 points. That's because 2 to the power 3 is 8, right? So we saw this, and then when we went on to 4 points, we quickly came across a case which could not be supported by linear equations. In other words, this sort of a dichotomy where these 2 points are yellow and these 2 are blue, you could never find a linear equation which can give rise to such a dichotomy. And we went on to see that mh of 4 was 14, which is actually less than 2 to the power 4, and therefore 4 was a break point for the hypothesis set of linear equations. We saw this in detail. Okay, let's now move on to what was actually the definition of Sauer's lemma. If mh of n has a breakpoint, that is mh of n is less than 2 to the n for some n, then beyond that n, mh of n has growth which is upper bounded by a polynomial of order dvc being the VC dimension. So to repeat, we are talking about the growth of the growth function. How does the growth function grow beyond its VC dimension? And what the Sauer's lemma tells us is that if the hypothesis set has a breakpoint, then beyond that breakpoint, the growth function grows like a polynomial. So why was this result so important? What was the importance of this result? This result was important because in the course of establishing the generalization bound, we ended up at an equation that looked like this. And we said that if this function has polynomial growth, then it could get killed by this negative exponent as n goes higher and higher. And this would in turn allow us to make E out as close to E in as we like. So it was an extremely important result because it helped us establish that E out could be made arbitrarily close to E in by increasing the number of training samples, right? And a key ingredient of that was the fact that MH grew like a polynomial. Okay. We are going to prove this result by induction. Now, I assume that most of you are familiar with what proof by induction entails, but that is how we are going to go about our business. Okay, this graphically shows what we are talking about. Okay, I have drawn the curve 2 to the power n. This brown colored curve is 2 to the power n, and I have shown the growth function of the hypothesis set of linear equations. So mh of 1 was 2, mh of 2 was 4, mh of 3 was 8, and then it started diverging from 2 to the power n, right? So this was the smallest breakpoint, and all of these were breakpoints as well, but we are going to refer to the smallest breakpoint as the breakpoint hereafter. If you had some other hypothesis with the same VC dimension 3, what would happen is till 3, these red dots would continue to fall on the curve 2 to the power n, beyond which they would diverge. So what we are going to be talking about now, what Sauer's lemma refers to is essentially the growth of these growth functions beyond the breakpoint. So how do they grow, or what is their behavior after they have crossed the breakpoint? It will not go down. Assume it's this way, right? So this is the behavior which we are interested in determining. Okay. Now, in order to do this, I want to define some terminology. Okay. We will define B of n comma k. B of n comma k is the maximum number of dichotomies possible on n points for any given hypothesis whose smallest breakpoint is k. Okay, so we could have, it's exactly the growth function mh of n, except that we are introducing a parameter k, and therefore we are defining this new notation. This new notation, once again, it's an important notation, so I will repeat it. B of n comma k, B of n comma k simply refers to the maximum number of dichotomies possible on n points for a hypothesis set whose smallest breakpoint is k. And here the word maximum essentially refers to the placement of points. So you remember how the growth function is calculated, right? So I give you n, you give me the placement of points, I give you the labelings, and then you come up with a hypothesis from your hypothesis set that supports that labeling. So the maximum number of dichotomies here refers to your ability to place the points in a particular manner. That's the word, that's what the word maximum refers to. It's basically the growth function. B of n comma k is essentially the growth function of a hypothesis set whose smallest breakpoint is k. We will call it Bn comma k. Okay. I'm now going to proceed to create a table of dichotomies or labelings possible on n points given k is the smallest breakpoint. And of course, we are interested in the region where n is greater than k, because if n is less than k, the number of dichotomies is going to be equal to 2 to the power n, so that is not interesting to us, and therefore we are going to be dealing with n greater than k. So let's create a sample table of these dichotomies. Okay, so look what I have done here. It's important to understand this in order to understand the Sauer's lemma. Okay, so I have points x1 through xn. These are n points, and these are labelings of those points. These are labelings or dichotomies of those points that are supported, right? So I have listed all of them here. Now, remember, if I say that K is a breakpoint, no subset of K columns out of n has all 2 to the K labelings. I hope you understand this. So what I am saying is that because K is a breakpoint, you cannot find n columns. You cannot find n columns out of, you cannot find K columns out of these n columns such that in those K columns you have all 2 to the K possible labelings. That's not possible because K is a breakpoint, right? So let's keep that at the back of our minds. But what we have here is the table of dichotomies. The number of rows in this table is what we have been calling, B of n comma K. Right? So these are labelings. I am going to divide these labelings in certain manner, but before I do that, I am going to sort of keep xn, the nth point, a little bit separate from the other points. So I have this thick black line right here, and this is the nth point, and these are the n minus 1 points. Okay. Like I said, I'm going to divide these dichotomies into 2 groups. Okay. Let me tell you what these groups are. The first group is called group S1, and let us say the number of rows in this group are alpha. So there are alpha number of rows in this group S1. What is this group S1? S1 is the group of all vectors of length n minus 1 that appear only once. Okay. So all vectors of length n minus 1 that appear only once in this entire table. Okay. What am I trying to say? Imagine a situation where you have n point. Okay. Let's say these are n minus 1 points and this is your nth point. I've sort of drawn it a little bit further for differentiation. You can assume that of all the dichotomies on these n points, there are some where there is a particular dichotomy on this n minus 1 points, particular labeling on these n minus 1 points, where only one possible labeling of this nth point would be supported. Right? So if this is blue, yellow, blue, this point can only be made blue. That is what I am talking about. Only one possible value of the nth point is possible for certain labelings of these n minus 1 points. There will be certain rows of that type. Of course, there will be certain rows of the type where for some values or for some labelings of these n minus 1 points, this point can be made either plus 1 or minus 1. Both of these dichotomies would be supported, right? So that would be the other set. But S1 is the group or the set of all vectors of length n minus 1 that appear only once in this overall table. In other words, for these rows, both values of xn are not possible. Only one value of xn is possible. Okay? Great. Of course, what is the other group? The other group S2 is the group of all dichotomies where both values of xn are possible. Okay? So, to illustrate, for example, this is one such vector where x1 through xn minus 1 took these values, and for those values of x1 through xn minus 1, both values of xn are possible. So notice that this is the same as this, and xn sub is there as minus 1 and plus 1 as well. Okay, so again, going back to this diagram, like I said, these are the dichotomies where for a particular labeling of these n minus 1 point, both labelings of n are possible. Okay. Now, because both labelings of n are possible, I have divided it into two groups. So, this is the set of rows where for the nth point we put minus 1, and these are the rows for which for the nth point we put plus 1, and this part of those rows are identical, right? So they differ, these two rows differ only in the last point, in the point n, right? So to recap, S2 is the group of all vectors of length n minus 1 that appear twice. One wherein xn has the label minus 1 and other where xn has the label plus 1. Right? Stare at this figure for a moment if you've still not understood what I am talking about. Okay, let's move on. The total number of rows, like I said, the total number of rows here is b of n comma k, and since the number of rows in group S1 is alpha and the number of rows in the group S2 is 2 beta, b of n comma k is alpha plus 2 beta, and the number of rows here are beta, obviously. So this is beta, this is beta, this is beta, this is beta. So this together is 2 beta plus alpha. Therefore, b of n comma k is alpha plus 2 beta. Okay, I am now going to estimate the values of alpha and beta in terms of this quantity b that I had defined. Okay, so I have drawn the same table once again. And the first claim I am going to make is that alpha plus beta is less than or equal to b of n minus 1 comma k. Remember the definition of b n k, it's the maximum number of dichotomies possible on n points. Okay, so this entire thing was b n comma k, and my claim is that alpha plus beta, let me remove this half. I am saying that alpha plus beta is less than or equal to b of n minus 1 comma k. Why is it less than n minus 1 comma k? Actually, that's by definition. What do I mean by definition? I mean, here are n minus 1 points. You have certain dichotomies, certain number of dichotomies on n minus 1 points. You know that k is the breakpoint. And by definition, therefore, these many number of rows is going to be less than or equal to b of n minus 1 comma k. In most practical scenarios, this would actually be equal, okay, but less than or equal to, without loss of generality, I can say that, because you may argue that, you know, these rows were chosen in a particular way with certain labelings of point of the point xn, and therefore it is conceivable that these number of rows is actually less than b of n minus k. But whether it is less than or equal to, it's certainly less than or equal to, okay. So, and that is simply by definition, because the definition of b of nk is the maximum number of dichotomies on n points. Here we are dealing with n minus 1 points. We are going to ignore the nth point entirely. These are dichotomies of n minus 1 points for sure. And therefore, by definition, these dichotomies, this number of dichotomies is less than or equal to b of n minus 1 comma k by definition. Okay. The second claim we will make is that beta is less than or equal to b of n minus 1 comma k minus 1. Now this is important. So let me hide all the other rows. Let me just stick with beta rows. And here is the logic or reasoning why beta is less than b minus 1 comma k minus 1. Okay. We are concerned with the labelings of n minus 1 point. So clearly the first argument is n minus 1. And our claim is that in these dichotomies on n minus 1 points, there cannot be k minus 1 columns with all 2 to the k labelings. So within these n minus 1 points, you cannot find k minus 1 points for whom all 2 to the k minus labelings are available in these beta rows. Why is that? Because if you had k minus 1 columns here which had all 2 to the k minus 1 labelings, by adding the nth point for which both labelings are available, we said for the nth point over here in this group, xn can be plus 1 as well as minus 1. It can be plus 1 and minus 1 both. You would, in this table, in this bigger table, you would have k points, the kth point being this one, such that all 2 to the k labelings are possible. Right? I'll repeat this argument. It can be a little bit confusing. The claim is that beta is less than b of n minus 1 comma k minus 1. N minus 1 is clear because we are only looking at the dichotomies on n minus 1 points. Right now, we are not bothered with the nth point. You're dealing with only n minus 1 points. So this number deals with n minus 1 points, and therefore the first argument is n minus 1. Why is the second argument k minus 1 and not k? That's the tricky argument. The argument goes as follows. We claim that among these n minus 1 points, there is no subset of k minus 1 points such that in those columns all 2 to the k minus 1 labelings are available in this group. Why am I saying that? Because if in this group you could find k minus 1 columns which had all 2 to the k minus 1 labelings on those k points, by adding this kth point, which is x of n, you would be able to have k points which have all 2 to the k labelings. Why is that? Because remember, this is one half of the group for which both labelings of the point xn are available, right? So these k minus 1 points plus xn standing as your kth point would give you k points. For in those columns, you would have all the labelings of k points in this group, right? And therefore k would not be a breakpoint of this entire set. That is the logic. And therefore this second argument over here has to be k minus 1. Okay. So we've established that alpha plus beta is less than this, beta is less than or equal to this, and therefore we have this identity b of n comma k is less than or equal to b of n minus 1 comma k, b of n minus 1 comma k minus 1. Why is that? Because this is equal to alpha plus 2 beta, right? This quantity is less than this alpha plus beta is less than this quantity, and beta is less than this quantity, and therefore alpha plus 2 beta is less than or equal to this plus this, right? Remember, I mean, I'll repeat because this can get a little bit tricky. I know that. This is simply alpha plus 2 beta. That's the total number of rows in this entire table, which is alpha plus beta, which is alpha plus 2 beta. We have shown that this is equal to alpha plus beta, obviously. We have shown that alpha plus beta is less than or equal to this. We have shown that beta is less than or equal to this, and therefore we have shown this particular identity. Okay, this identity is going to come in handy in the proof of Sauer's lemma. So here is a theorem. Here is a theorem that we are going to prove. We are going to prove that b of n comma k is less than or equal to summation of I going from 0 to k minus 1, n choose I. Okay, so this is a summation of n choose i's with I going from 0 to k minus 1. And as you can see, n appears over here, and k appears in the limit of the summation, right? So, you know, again, I mean, I hope everybody knows that n choose I is essentially n factorial upon n minus I factorial, right? You know this. So that's what this is. And this is what we are going to prove. This is what we intend to prove. And the proof, like I said, is by induction. So we will assume this result. We will assume this result for n minus 1 and k minus 1. And then we will show that it continues to hold for n and k. That's how induction works. And plus, of course, you have to prove the boundary conditions. So prove that it holds for some small values of n and k. Right? Okay. So that's how we are going to go about our business. To recap, here is how the proof by induction is going to go. We want to show this. Okay, we want to show that b of n comma k is less than or equal to summation of n choose i's. Okay, in order to show this by induction, we assume that this thing holds for n minus 1 k and n minus 1 k minus 1. So what would be b of n minus 1 comma k, assuming this holds? It would be that b of n minus 1 k is less than or equal to summation I going from 0 to k minus 1 of n minus 1 choose I, right? And this would be, you just substitute n minus 1 and k minus 1. So the summation goes to k minus 2 now, and instead of n you have n minus 1. So these are the two assumptions we are going to make. These are the two assumptions that we are going to make. We are going to assume that the theorem holds for n minus 1 and k minus 1. And by using this identity that we just proved in the previous slide, we are going to show this thing. This is what we want to show, right? So this is how induction is going to work. Let's go on. So I'm now actually looking at b of n minus 1 comma k and b of n minus 1 comma k minus 1. Okay, so I'm going to substitute these things here. Okay, I'm dealing with the right hand side. So what is my right hand side? My right hand side is simply the summation I going from 0 to k minus 1 of n minus 1 I, and plus summation I going from 0 to k minus 2 of n minus 1 choose I. So once again, this was b of n minus 1 comma k, and this was b of n minus 1 comma k minus 1. And I've just added these two together. And this is what it equals to. For the first summation, I have pulled out I equal to 0. So when I equal to 0, anything choose 0 is 1. So that is this one. And then the summation goes from I equal to 1 to k minus 1. This is the first term. Okay. And the second term I have kept as is. Right? Okay. Simplifying this thing further, this I have written as is, and this term I have changed the counter for the summation. Instead of I going from 0 to k minus 2, I have taken I going from 1 to k minus 1, and I have changed in the term which is being summed, I have changed I to I minus 1. So when I equal to 1, this is equal to 0, which is the same thing as I being equal to 0. And when I equal to k minus 1 over here, this would be k minus 2, which is the same thing as having k minus 2 over here. So I have just changed the index of summation. Making the corresponding change in what is being summed. Right? So this is exactly equal to this. only change is the index of summation was changed. Now, since both of these summations go from I equal to 1 to k minus 1, I can actually group these two terms. So I'm taking the summation outside and grouping these two terms. This term is this and this term is this. And I've just sort of taken the summation out because both summations go from I equal to 1 to k minus 1. Okay, now my job is to simplify this. Like I said, we all know that A choose B is equal to A factorial upon A minus B factorial multiplied by B factorial. You could use this over here and go through, the process of grouping terms, etc. in order to simplify this. But we are going to simplify this by making a simple combinatorial argument. Okay. Now, both these terms are n minus 1 choose I and n minus 1 choose I minus 1. Let me give you an analogy. Let us say you have n students in the class. Okay, let's not choose n. Let's say x. Let's say you have x number of students in the class and that class includes me, for example. And from that class of x students, which includes me, you have to choose 10 students. How many ways could you do that? The number of ways in which you can choose 10 students out of those x students would be the number of ways in which you can choose 10 students out of x minus 1 students, leaving me out. Leaving me out from the remaining x minus 1 students, you choose 10 students, plus the number of ways in which you can choose 9 students from the remaining x minus 1 students, while definitely including me, right? To repeat, if I have x students in a class that includes me, and if I had to choose 10 students from that class, the number of ways of choosing 10 students from that class would equal to the number of ways of excluding me and choosing 10 students from the remaining class, and including me as the 10 students and choosing 9 students from the remaining x minus 1 students in the class, right? That is exactly what is being done here. Here you have n minus 1 students in the class, okay? First you choose I from those x minus 1 and then you choose I minus 1 from those n minus 1, and therefore this is essentially just n choose I. Right? I hope you understood the combinatorial argument. If you've not understood the argument, you can plug in the meaning of n minus 1 choose I, like I said, the factorials, group the terms, and you could simplify to this result. So this is 1 plus summation I going from 1 to k minus 1 of n choose I, and now I once again bring this 1 in here. And this is simply equal to summation I going from 0 to k minus 1 of ni. Right? So we have proved that this is equal to this. Okay. So here we are. We assumed that this is less than this. We assume that this is less than this. The summation of these two terms we showed is this, and therefore using this identity we have shown that b of n comma k is less than or equal to summation I going from 0 to k minus 1 of n choose I. Right? This is where we are. Induction also requires us to deal with boundary conditions. So we have to compute the bounds for small values of n and k. So I have drawn a table over here, k going from 1, 2, 3, 4, so on, n going from 1, 2, 3, 4, so on. Let's see the first column. Okay, let's see the first column. If k is 1, what it means is that no single point, no one point can assume both values in the labelings that are possible. Okay, so if you had n points, let us say if you had 5 points, let us say if you had 5 points, n equal to 5, what it means is that you could have one set of labeling for the 5 points and you could not have another labeling on those 5 points, because if you had a second labeling, that second labeling would differ from the first labeling in at least 1 point, but you know that k equal to 1 is a breakpoint, so no single column can have both values, right? So therefore, if k equal to 1, for any values of n, the upper bound b of n comma k is going to be 1. In scenarios where k is bigger than n, you would have all 2 to the n dichotomies possible. But let us use this recursion, b of n comma k greater than b of n minus 1 comma k plus b of n minus 1 comma k minus 1. Let's use this recursion to fill in these values over here. This would be 3, this would be 4, and so on and so forth. These would be the bounds, and you can verify that these bounds hold for these small values of n and k. Right? So the boundary values are proved. I actually went through that exercise and I filled in some more values and I verified that these indeed are bounds. These indeed are bounds for the number of dichotomies possible on n points with k being the breakpoint. Okay, so the boundary conditions continue to hold. The result on b of n comma k being less than this summation of n I, this holds for these small values and therefore the induction is proved. Great. So we have therefore proved Sauer's lemma. We have shown that b of n comma k is less than summation I 0 to k minus 1 ni. We showed this by induction. And this thing is really a polynomial of order k minus 1, which is indeed the VC dimension. Okay, I leave it as an exercise for you to show that the highest order of n in this expression is going to be k minus 1. Okay, and k minus 1 is indeed the VC dimension. So what we've said, what we have effectively proved is that b of n comma k, which is the maximum number of dichotomies on n points where k is a breakpoint, is less than a polynomial of order equal to the VC dimension. That's the Sauer's lemma that we have just proved. This result once again was important because, like I said, while we were deriving the generalization bound, we had ended up at a place like this, and now that this grows slower than a polynomial, you are assured that E out can be made arbitrarily close to E in. Okay, so that's the proof of Sauer's lemma. Let's now move on to the VC dimension of the binary linear classifier. This was another important result that we assumed when we were talking about this a few lectures ago. So what is the result in question? The result that we want to prove says that for the general d-dimensional space, the VC dimension of the binary linear classifier is equal to d plus 1. In other words, equal to the number of dimensions plus 1. That's the result that we want to prove now. Okay. We are going to do this by showing two things. We are going to show that dVC cannot be less than d plus 1. So the VC dimension cannot be less than d plus 1. And we will show that dVC cannot be greater than d plus 1. Okay, so in the d-dimensional space, this is the dimensions of the space that we are talking about. We are talking about the binary linear classifier, and we are going to show these two things. And if we prove these two things, all that it will tell us is that dVC is equal to d plus 1, right? This is the only possibility that remains if we prove these two things, and that's how we are going to go about it. Okay, first let's look at the proof of dVc cannot be less than d plus 1. Okay, dVc cannot be less than d plus 1. This is the Vc dimension. Okay, in order to do this, we need to show that there exist d plus 1 points that support every labeling. Okay, so I will give you placement of d plus 1 points such that no matter what labeling you give me, I will always be able to find a linear classifier that supports that labeling. That is what I am going to do. So I have to give you the placement of these d plus 1 points. Okay, let's look at the matrix, vector matrix equation. These are the outputs y1 through yn. This is the matrix of inputs, and these are your weights, right? So the resulting value of y is essentially this matrix multiplying the vector of the weights. We have seen this earlier when we did the binary linear classification. Now, what I want to be able to prove really, is that every labeling, no matter what plus minus 1 values of y3, y1 to yn you give me, so you could give me y1 equal to either plus minus 1, y2 equal to either plus minus 1, etc., etc. No matter what labeling you give me for the y's, I can always find w's such that this labeling is supported. Okay, and what I have in my hands are the values of the x's, which are the coordinates of the points in question, right? So I have to find the x's such that no matter what labelings of y you give me, I can always find a w. In other words, I can find a hyperplane. These are the parameters of the hyperplane. These are the constants of the hyperplane, such that every labeling is supported, right? And I am going to choose n equal to d plus 1 to show this. Okay. So how do I choose my n equal to d plus 1 points? I am going to choose them in the following manner. Okay. So I am going to choose the first point x to have all coordinates equal to 0. The second point to have the first coordinate equal to 1 followed by all others equal to 0. The third point such that the first coordinate is 0, the second is 1, rest are zeros, etc., etc. So this subdiagonal has all ones, and there are all zeros here, and the first column is of course 1 because the first column multiplies w0, right? So this is how I am going to choose my points. Now, no matter, here is what happens now. Okay, before I show you what happens, let me elaborate on the selection of these points. My first point is the origin, all zeros, and then the remaining points I essentially choose at a distance of 1 along each of the axes. So in 3 dimensions, these are the 4 points I choose: origin, 1, 2, and 3. So total of 4 points in the 3-dimensional space. So these are 4 equal to 3 plus 1 points. Okay, so this is the kind of selection of points that I am going to do, and my claim is that once I select the points in this manner, no matter what labels you assign to each of these points, I will be able to find a hyperplane. I will be able to find the values of w so that those labelings will get supported. Okay, that dichotomy that you tell me will get supported. Okay. Now, why have I chosen the values of x's in this manner? The reason I have chosen them in this manner is that this matrix, this is a d plus 1 by d plus 1 matrix. There are d plus 1 columns, right? There are d plus 1 columns because it multiplies this vector, and there are d plus 1 rows because there is a total of d plus 1 points that I'm talking about. So this is a square matrix, and this matrix is invertible. This is an invertible matrix. I can find its inverse. Okay. And if I can find its inverse, what I am saying is no matter what values of yi you choose, you can always find the set of weights, because let's say that this, in a vector matrix notation, this is y hat equal to x w hat. Hat I am using for the vectors, and therefore w hat is equal to, x hat inverse y hat. So as long as the matrix X is invertible, this exists, and you can find the corresponding values of the weights W, which define your hyperplane. So what I am saying is that no matter what values of yi you choose, whether plus or minus ones, you can find a set of weights because the matrix is invertible. You can choose yi is equal to plus or minus 1 as per whatever labeling you want, and you can find the corresponding weights and the hyperplane. Right? So you can plug the values of yi equal to those labels. So if somebody tells you that this label is plus 1 or minus 1, you can actually choose yi equal to 1 or yi equal to minus 1 as the case may be, and get the values of weights. So clearly with such a selection of points, d plus 1 points, you can support any dichotomy, right? And effectively what we have proved is that the VC dimension dVC is, going back to the previous slide, what we have effectively proved is that dVC cannot be less than d plus 1, right? Okay. Let's move on. Let's prove that dVC cannot be greater than d plus 1. Okay. So when you say dVC cannot be greater than d plus 1, what do I have to show you? I have to show you that no matter which d plus 2 points you give me, I will always be able to provide you a labeling that you cannot support. Right? I'll repeat. If I have to prove that dVC cannot be greater than d plus 1, I have to show you that you may give me whatever placement of points you want. I will give you a labeling such that you will not be able to find a hyperplane that creates that sort of a labeling. Okay? That is what we are going to prove. So let's go back to the vector matrix equation that we had. The vector y equal to vector x times vector w. And what I am going to do is, let us add an additional point in addition to d plus 1 points. So here n equal to d plus 1, as was the case in our earlier slides, right? We took d plus 1 points and we added an additional point in addition to your d plus 1 points. Okay, I call that point j and I say yj equal to 1, xj1, xj2, so on and so forth till xjd. And this is going to, of course, multiply this weight vector. Now, this last vector can always be written as a linear combination of these d plus 1 vectors. Okay. Why is that? If this vector cannot be written as a linear combination of these vectors, it means that these points that you chose were such that all dichotomies would not be supported on these points themselves. So the question of me giving you an additional point and an additional labeling for that additional point does not arise. Okay. If you wanted all labelings to be supported on these d plus 1 points, these vectors would have to be linearly independent. And if they are linearly independent, then any additional vector that I create can be written as a linear combination of these vectors, right? Okay. So effectively what I am saying is that xj, this xj is this last vector. This vector xj is a linear combination of these xi's, where I runs from 1 to d plus 1. Okay, so this is this goes from 1 to d plus 1, and ai's are the corresponding coefficients of that linear combination, right? Okay. Now remember over here our vector y is equal to vector x times vector w, right? Matrix x times vector w, and here my row xj, my vector xj, I am writing as a linear combination, of the earlier d plus 1 vectors. And the reason I can do that, the reason why this can be expressed as a linear combination of the other vectors, is because this is the d plus 2th vector, and all I am saying is that if it cannot be written as a linear combination of these, it means that these were linearly dependent on each other, which means that even amongst these, all labelings cannot be supported. Right? You remember, if you had a labeling like this, 3 points in one line and fourth point over here, even on these points, all labelings cannot be supported. So for example, if this was blue, if this was yellow, if this was blue, there was no line that would create that sort of a separation, right? So this is ruled out, and therefore xj can be written as a linear combination of the other d plus 1 vectors. Okay. What does that mean? We will now create a labeling. I will now give you a labeling or a dichotomy, sign assignments of yj, which cannot be supported. If xj is a linear combination of the other xi's, I can write yj equal to w transpose xj, right? Yj, my jth output is w transpose xj. This has to be a subscript, and by plugging in xj equal to summation of ai xi, this actually becomes equal to this, right? Okay, and therefore my yj is a linear combination of the other yi's, because this is equal to yi, right? Okay. Now what we are going to do is we are going to say that if these yi's are selected such that the sign of yi is the same as the sign of ai, and yj is selected as -1, then such a dichotomy cannot be supported. Okay. Now when I said that xj is a linear combination of xi's, these scalars ai's had a certain sign. I mean, some of them could be 0, but we forget those. The non-zero ai's are either positive or negative. And what I am saying is I am giving you a labeling which says that the sign of yi has to be equal to the sign of ai, and the sign of yj has to be equal to -1. Why is this not supported? Because when the sign of ai and yi is equal, all of these become positive, and therefore the sum of several positive quantities cannot be equal to a negative quantity. So this is an example of a dichotomy that cannot be supported if you have d plus 2 points, right? Okay, sorry about this thing. I mean, this should be a transpose and this has to be a subscript, but I think this is pretty clear. Let's now move on to the last topic of this session. I'm going to talk about constraint optimization. We saw Lagrange multipliers in the earlier discussion where we talked about regularization. But let me give you the big picture first. You know, we've seen that learning essentially constitutes solving an optimization problem. So you have certain data, you have certain model parameters, and the values of those parameters have to be determined. and in some way or the other, this ends up being an optimization problem where you are probably trying to minimize the error in certain sense, right? So effectively, any training algorithm essentially ends up as an optimization problem, and you have to solve the optimization problem. If it is an unconstrained optimization, if it's a straightforward optimization, you could probably choose the mean square error as your error metric, which you want to minimize. And you could do it with the simple gradient descent that we discussed in the context of linear classification or in the context of linear regression, right? So this was those were example of unconstrained optimizations, but they were optimizations. In the context of regularization, we ran into a constrained optimization problem where we used the Lagrange multipliers. So the problem that we faced was as follows. We had to optimize some function of the model parameters subject to a constraint that said a function of the model parameters was equal to 0, and your job of course was to find the values of the best model parameters subject to this constraint. So you had to optimize a function subject to a constraint and find the values of the model parameters for this particular constrained optimization problem. And the way we did it, I mean, we showed a pictorial proof. The way we did this was by showing that if we had to optimize a function subject to a constraint like this, the gradient of this function, would have to be aligned, would have to be a multiple of the gradient of the constraint. You remember in the last lecture I showed you why this is the case, and the constant of proportionality was lambda. In our case we used it as lambda over 2n or whatever, but effectively it's a constant, and this was the Lagrange multiplier. Okay, so this was the Lagrange multiplier. So we have seen this. Now what do we have here? We had this equation and we had this equation, which was basically the constraint, and you will notice that these are actually m plus 1 equations in m plus 1 unknowns. So if the size of the vector w was m, because you have gradients, this is going to be a vector, right? This is a gradient of a scalar, but that's a vector. This is, of course, gradient of GW is going to be a vector. So this is a vector equation. And what it means is that it has to be satisfied for each element of those corresponding vectors, right? And therefore, this is actually m equations and this is one equation. So you effectively have m plus 1 equations in m plus 1 unknowns. If this is cluttered too much, let me just remove the clutter. These are m equations, because this is a vector equation and this is one equation. So totally m plus 1 equations in m plus 1 unknowns. What are the m plus 1 unknowns? The size of w is m, so those are the m unknowns, and lambda of course is one additional unknown that you are now talking about. So m plus 1 equations in m plus 1 unknowns. Okay. What if we had multiple constraints? In the subsequent lectures, remember I am trying to use this opportunity to prep up for what is going to follow, the models and techniques that we will be talking about in the subsequent many lectures. What if you end up with multiple constraints? So you had, I'm just going to take two constraints here because it extends to multiple constraints. Let's say you had GW equal to 0 and small f of W equal to 0, two constraints, multiple constraints. What you would end up having are, the first would be two Lagrangians. For G I am using lambda, for F I am using mu, right? Both lambda and mu are some constants, and you could write an equation like this. if you had multiple constraints, because for these two constraints you would effectively be creating a plane, and the tangent to that plane would have to be a multiple of the tangent to f. Okay, so this would be one equation that you had, and then plus these two equations. So you would effectively end up with m plus 2 equations in m plus 2 unknowns. M plus 2 unknowns being the m components of w plus lambda and mu as your other unknowns, right? So this is what would happen. If you wanted to dig in a little bit deeper as to why this happens, effectively what's going to happen is that if you had f that you tried to that you were trying to minimize or optimize, and if you had these two constraints together would create a hyperplane. Okay, not necessarily not a hyperplane, it would be a surface, and the tangent to this surface would have to be a tangent to this curve f as well, and the tangent to this surface you could write as a linear combination of the gradient of g and the gradient of small f, and that is why this equation comes about. If you wanted to dig in a little bit deeper, I suggest you go and take a look at this, but I want to essentially summarize how you would go about if you had multiple constraints. So if you had a constraint optimization problem with where you had to optimize, minimize or maximize a function subject to multiple equality constraints, this is how you would go about doing it. You would configure it as m plus 2 equations and m plus 2 unknowns, or however many constraints there were, and these would be the equations that you would be dealing with. Now, we had this case earlier, and how would you solve these? I mean, how would you generally go about solving these? Well, closed form solutions are often not possible. I could always create some very simple equations for the function to be optimized and of very simple equations for the constraints, and then you would be able to work out closed form solutions. But most often in practical scenarios, closed form solutions are not possible. Okay, closed form solutions are not possible, and therefore iterative approaches have to be used, and that is exactly what we did to find lambda when we were talking about regularization. Remember, in regularization we said that you cannot get a closed form expression to find the value of lambda, and you sort of iteratively try to find the best possible value of lambda. That is essentially what has to be done, and you have to employ things like grid search or other gradient based methods. There is also something called the Newton-Raphson method if you are interested in digging into this a little bit further. But for all of these, libraries are already available in Python. So, or in any other framework that you are using. The bottom line, that the point I want to make is there exist numerical methods to solve constrained optimization problems. That's the point I'm trying to make. So if you had a problem, if you structured it as a constrained optimization problem, your next step would be to use one of these available methods, available libraries to solve that constrained optimization problem. And that is going to happen quite frequently in what is going to follow in this series. Okay, great. Okay, KKT conditions. The KKT conditions or the Karush-Kuntakar conditions are essentially a generalization of the equality constraints that we saw earlier. KKT conditions essentially deals with a combination of equality and inequality constraints. Of course, this is more general than an equality constraint. So what if you had to optimize a function? Subject to inequality constraints? So far we were looking at equality constraints. What if you had to optimize subject to inequality constraints, and perhaps you could throw in some equality constraints as well? So this is the most general situation, and these are known as the KKT conditions. So how do you go about addressing these. Again, very similar to what you did with Lagrange multipliers earlier, you create this equation, right? You create this equation, and in addition, you have these constraints like these. And again, the point I want to make is I don't want to, it's beyond the scope of this lecture series to get into the details of how these conditions are solved, but suffice it to say for now that there exist numerical techniques, there exist libraries that will allow you to solve problems like these. What actually happens, just to take this a step further, you can have what are known as dual feasibility constraints, and you can also have something called a complementary slackness. So you could say that lambda times g is equal to w, so either lambda has to be greater than 0 and g has to be lambda is greater than 0 and g is 0, or vice versa. So you can impose conditions like these depending upon what your problem is, and then proceed to solve them. And one of the methods, one of the numerical techniques that is used is called the SQP technique, sequential quadratic programming technique, and that is often used to solve the KKT conditions. That is often used to optimize subject to KKT constraints. Okay. Again, I'll repeat. Why am I throwing out this terminology without going into the details? Because these are the search prompts for you. Tomorrow, if you are, you run into an optimization subject to inequality constraints, as you would subsequently, you should know at the back of your mind that there exist numerical techniques, iterative techniques to solve such optimization problems. And if you wanted to dig a little bit deeper, these would be your search prompts, KKT conditions, SQP, so on and so forth. Okay, so our job in the subsequent lectures will pretty much involve getting to a point where you determine what has to be optimized and determine the equality or inequality constraints, and then we are assured that once we get to this stage, there exist libraries, there exist techniques that will allow you to obtain the optimal W. Okay, so we have that reassurance. Okay. So here is what I want to do. I want us to go over an exercise. I want you to go over an exercise where you create a constrained optimization problem. You could take any complicated function of multiple variables that you want to optimize, let's say minimize. You give some arbitrary inequality constraints, and you find the best Python library to find a solution, and you actually go about finding you feed the function you want to optimize, you feed the constraints that you have, and you obtain a solution. What is the purpose of this exercise? The purpose of this exercise is to give you some sort of a reassurance that if you ever ran into a constrained optimization problem, you have libraries out there that will find a solution for you. Okay, so that is the exercise. I leave it to you what function you want to optimize and what inequality constraints you want to impose. Okay, but go over this exercise. I know most of you are experts at using Python libraries, so find the correct library and go about and find a solution. Okay, so that is the exercise. Okay, this was the slide that we started with. I told you we were right here. We have covered the two important proofs for AI specific results that we used in our theory of learning. Okay, that was the first result was the Sauer's lemma. The second one was the VC dimension of binary linear classifier. We've gone over those two proofs, and we have also talked about and given references to some of the other results that we used. And from the next lecture onwards, we will start looking at different models and techniques. We are done with the theory of learning that we had planned for this course. This is a pivot point, and from here onwards, we will start looking at models and techniques. We will look at neural networks, we will look at SVMs, we will look at Markov models, we will look at decision trees, and as we have been doing so far, we will look at all of them in great detail. Okay, but those are models, those are techniques, and those will be used in various problems. So that's the plan ahead. We are probably around the halfway mark, and there are numerous models and techniques that we will be studying from this point onwards. Great. So that brings me to the end of this lecture, but I am going to leave you with some reading material and some thoughts. Now, I came across a small interesting video. I am going to put this link in the description and you can take a look at this. This is a 3 or 4 minute video that talks about the state of art as far as AI is concerned, particularly in reference to language models. Okay, but take a look at this YouTube video. And like I said, the rest of our series is going to we are going to be concerned with various models that learn and learning techniques, and it's also going to it's got to do with implementations that are already available, and we will also deal with certain heuristics. So it's a change from the way, or it's a change from the topics that we have dealt with so far, but it will be advanced models, advanced learning techniques. That is what finally AI is all about, and that's what's going to be the subject for the subsequent lectures. Great, that's pretty much it. Thank you, and I look forward to seeing you for the next lecture.